Okay, we are looking at the Chapter 9 valence bond theory and molecular orbital theory homework. So in number 1, we're supposed to give the hybridization of the underlined atoms. So in A, this nitrogen, since it has 4 pairs, a bond, a bond, a bond, and a lone pair, each of these counts as a pair, it's going to be sp3 hybridized. In this case, the carbon has a single bond, and a double bond. That counts as 3 pair, so it is sp2 hybridized. So remember, a single bond counts as a pair, a double bond counts as a pair, a lone pair counts as a pair, and a triple bond counts as a pair. So here, this carbon has 1, 2, 3 pair, so it is sp2 hybridized. So I kind of think about it this way. 3 pair, spp, there's 3 letters, sp2 hybridized. This carbon has 2 pair, so it is sp hybridized. Now, for letter B, I forget. Let me take a look here and see what the which ones were supposed to be underlined, because I forgot to underline them. Okay, almost there. Okay, there's the homework. And let's take a look here. So I was supposed to have underlined this carbon, and this carbon. So this carbon is sp3 hybridized because it has 4 pair. This is sp2 hybridized, and this is sp2 hybridized. Okay, so that's number 1. Number 2, we're supposed to give the electron pair geometry and molecular geometry for each of the underlined. Well, to do this, we have to get the Lewis structure of each of these. So of course, we're going to start with counting electrons, deciding which carbon or atom is in the middle, and going from there. So this is going to have 4 electrons for the carbon. For the selenium, it's going to have 6 electrons, so that's 6 times 2. So here we're going to have a total of 16 electrons. 12 plus 4 is 16. Let's see. Just trying to change my screen so I can see what I'm doing here. All right. For this, we're going to have 6 plus 2 times 6 for 18 electrons. For this, we're going to have 4 plus 2 plus 6. So that's 12 electrons. And for this, we're going to have 5 plus 4 times 1. 4 of these times 1 each. And then minus an electron for the positive charge for 8 electrons. So here, I know that this is going to look like this with 16 electrons. That way I get I get an octet on carbon and my octets on seleniums. And here I know that this one is going to look like this. So I need 18 electrons. And I know this one is going to look like this. And I know this one is going to look like this. Now the last one, if I'm going to draw the Lewis structure, I need to at least include brackets and the charge on the outside. These don't have charges, so they don't need brackets. Okay, what is the electron pair geometry for each of these? EPG. So here, since we have two pair, it's going to be linear and 180 degrees. This, since it has three pair, it's going to be trigonal planar and 120 degrees. Here, since it has three pair, it's going to be trigonal planar and 120 degrees. And here, since it has four pair, it is going to be tetrahedral and 109.5 degrees. Now, what is the molecular geometry of each of these? Well, this is still linear, 180 degrees. This, however, is going to be bent 120 degrees because the molecule really looks like this, which looks more like it's bent than anything else. Here, this one is going to be trigonal planar. (120 degrees), so it's going to look like this. And this last one's going to look tetrahedral, so it's going to look like this. So we would say tetrahedral, 109.5 degrees. And that's number 2. Okay, for number 3, decide if for each if cis and trans is possible. If so, draw the other and label each of them and give the hybridization of each carbon. So the hybridization of this carbon is sp3. This one is sp2. This one is sp2, sp3, and sp3. Here we're looking at sp2, sp2, and sp3. Here we're looking at sp2, sp2, sp3. So those are all the hybridizations. Now, for cis and trans to be possible, you have to have a double bond, and you have to have two hydrogens bonded to the carbons of the double bond, and exactly one hydrogen to each carbon. So if we take a look, we do have a double bond. Each has exactly one hydrogen, so this has a cis-trans possible. Now, if I want to draw the other one, what I do is simply switch to the pieces on one side of the double bond. When I say one side of the double bond, I mean for one of the carbons, switch to two pieces that are attached. So here, I'm going to keep these two pieces the same, and I'm going to switch these two pieces. So you can see I've taken this CH2, CH3 and put it on the top, and this H and put it on the bottom. So that's what I mean by switch the pieces on one of the carbons. Now this one is the cis, and this one is the trans. So here, when the hydrogens are on the same side of the line, if you draw a line through the double bond, if the hydrogens are on the same side, it's cis. So here, we do have a hydrogen on this carbon, but we don't have only one hydrogen here. So here, no cis-trans. Again, you need exactly one hydrogen on each carbon, not two on one of them. That won't work. Here, is cis-trans possible? Well, that carbon has a hydrogen, exactly one. This carbon has a hydrogen, exactly one. And so cis-trans is possible. We can see right away that this is the cis. Now to get the trans, I'm going to switch these two, put the Cl down here and the H up there, and keep the other two the same. So this one is the trans, because the hydrogens are on opposite sides. Were we to draw a double bond, a line through the double bond that's parallel with the way the double bond looks. Now, what is the hybridization of the cis versus the trans? And the answer is they're exactly the same. The hybridization does not change. So this is sp3, sp2, sp2, sp3, sp3. And down here, this is still sp2, sp2, and sp3. Boom. Okay, number 4, sketch the MO diagram for O2 plus. What is the net number of sigma bonds and pi bonds? What is the overall bond order? How does the bond order change from O2 to O2 plus, and is it paramagnetic? So there are 2 orbital diagrams you need to know, MO diagrams. One is what I call the Christmas tree, because it kind of looks like a Christmas tree. And the other one I call the palm tree. So both have a trunk of 4 lines, and the Christmas tree looks like that, and the palm tree looks like that. So what do you use these for? The Christmas tree is used for all elements like H2, all the way up to C2. And this one is used for N2, O2, and F2. Okay, so we have O2, which means we need to use the palm tree. Now, what do each of these little lines represent? They represent an orbital, a molecular orbital. This one's a sigma 1s. This one's a sigma star 1s. This one's a sigma 2s. This one's a sigma star 2s. Star means anti-bonding, and if there's no star, it's a bonding orbital. This is a sigma 2p, and this is a sigma star 2p. You'll notice that for every bonding molecular orbital, there's the anti-bonding in this case. So this is a pi 2p, and this is a pi star 2p. Pi 2p, pi star 2p. Now, when we look at O2, it's going to have 8 times 2 electrons for 16 electrons total, because its atomic number is 8. Okay, so we have to put 18 or 16 electrons into here for O2. And for O2 plus, it's going to have 1 less electron. So we're going to have 15 electrons. So let's draw this showing the 15 electrons. So I'm going to put it in to the more stable molecular orbitals first, which are lower on this drawing. 1 up first and then 1 down to pair them. And we can see we have 2, 4, 6, 8, 10, 11, 12. Notice I separate them because these are similar energy orbitals, molecular orbitals. So you put 1 into each molecular orbital first before pairing. So now we have 12, 13, 14, and 15. So those are your 15 electrons for O2 plus. So what's the net number of sigma bonds? So the net sigma bonds would be equal to 1/2 of the bonding sigma electrons minus the anti-bonding sigma electrons. Okay. And the reason this is the case is because you need 2 electrons to make a bond. So if you have 2 bonding electrons here, 1/2 times 2 is 1 bond. But for every 2 bonding electrons, 2 anti-bonding electrons can essentially cancel them out. So let's look at all of the bonding sigma electrons. There's 2 right there. There's 2 right there. And there's 2 right there. So we have 6 bonding sigma electrons. Now remember, the stars are the anti-bondings. So how many stars do we have? We have 2 here, 2 here, and that's it. So we have 4 total. So the net number of sigma bonds is 1. Now, pi bonds, it's the same thing. 1/2 of the bonding pi electrons minus the anti-bonding pi electrons. So, how many bonding pi electrons? 1, 2, 3, 4. How many anti-bonding? 1. So here, 4 minus 1 is 3. 3 times 1/2 is 1.5. So that's the net number of pi bonds. So what is the bond order overall? It's the sum of 1 plus 1.5, which is 2.5 for the bond order. Okay. How does the bond order change from O2 to O2 plus? Well, here, if we look at O2, we'd have to put another electron there for 16 electrons. So what would change in all of this? Well, for O2, we would still have 1 sigma bond, but we would have -2 here for 1, and we'd have a bond order of 2. So that's O2, and this is O2 plus. So in going from O2 to O2 plus, you can see that the number of net pi bonds increases by half, and the bond order increases by half. And is this O2 paramagnetic? Yep, it is paramagnetic because it has this lone electron here. What about O2? Well, it's got 2 lone electrons, so it's also paramagnetic. Okay, and that is number 4. Number 5, we're supposed to get the bond angles here, the hybridization, and then compare them for each of these. So we already know that SO2 looks like this. So you can see I'm not really rehashing how to get the Lewis structures for each of these. SO3, that's going to have 24 electrons. So this is the best for that. And SO3, well, we're going to have the same as that, but 2 more electrons. So for SO3, we're probably going to do something like this. Because this has to have 2 more electrons than that. Now, of course, we have to put the 2 minus on the outside. And SO4 is going to look like this. These are going to give the best overall formal charges. And actually, I need to redraw this one because I look at it and I realize the formal charges here are 0, 0, 0, and -2. And that's not very good. So what would be better here is if we did this. And that way we get formal charges of -1, -1, 0, and 0. If we're going to have a negative formal charge, we want it to be on the most electronegative atom. Okay, so what's the hybridization of this guy? It's got 3 pair, so it's sp2 hybridized. This guy, it's got 3 pair, so it's sp2 hybridized. This guy's got 4 pair, so it's sp3 hybridized. This one's got 4 pair, so it's sp3 hybridized. So what is the bond angle for each of these? This is about 120 degrees. This is about 120 degrees. This is about 109.5 degrees, and this is about 109.5 degrees. So do they all have the same hybridization and the same bond angles? And the answer is no. However, SO2 and SO3 do, and SO3 2 minus and SO4 2 minus do have the same bond angles in hybridization. All right, number 6. For N2 plus and N2 minus, we're supposed to get the electron configuration, the magnetism, the net number of sigma bonds, the net number of pi bonds, the bond length and bond strength. So here we need to count electrons. This is in group 7A, so it's got 7. I should say this is, I'm sorry, this is atomic number 7. So it's got 7 electrons for 1 nitrogen. So this is going to be 14 electrons. This one, since it's got a positive charge, it's going to have 1 less electron. Because that has a negative charge, there's 1 more electron. So that's 15. So let's start with the 13 electrons since it's the fewest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So for the electron configuration, this is the core. So we can write core, and then we have parentheses, sigma 2s2, parentheses, sigma 2s star 2, parentheses, sigma 2p 2, and then parentheses, pi 2p 3. So notice we combine these together. We don't write them separately because they're the same energy. Now, how is N? That's for N2 plus. Now, what would N2 look like? Well, it would be the same, except it would be pi 2p4. And what would N2 be like? Well, it would be the same. So this is a N2, and this is N2 plus, and N2 minus would be pi 2p4, and then pi star 2p1. Now the magnetism, we can see that for N2 plus, this is going to be paramagnetic. But when we add another electron for N2 minus, this one's going to be diamagnetic because everything's paired. And then when we add another electron, it'll go here as a single, and this will be paramagnetic again. Net number of pi or sigma bonds. So we can see these two cancel because here's the bonding pair and here's an anti-bonding pair, so they cancel. Bonding, anti-bonding, they cancel. Here's a bonding pair, so that's 1 sigma bond for N2 plus. And that's going to be 1 sigma bond for N2 minus and N2. Now, net number of pi bonds, let's take a look. We've got 2, 3, so that counts as a bond and a half. So for N2, we've got a bond and a half. When we put another electron here for N2, we're going to end up with 2 pi bonds. And then when we put another electron in over here, we'll have 4 bonding electrons and 1 anti-bonding for a net of 3 bonding electrons. And remember, 3 bonding electrons don't equal 3 bonds. They equal 1.5 bonds. So what is the bond order? It's going to be 3, 2.5, and 2.5. Now, as far as bond length goes, what will these be compared to one another? Well, this one's going to be the shortest. Why? Because if the bond order is larger, it will have a shorter bond length. And these will be longer, and we expect these to be the same because they're both 2.5s. Okay. Now, bond strength. We expect this to be the strongest because more bonds is a stronger bond. And this is supposed to be weaker, and it should be about the same as this one. And that's number 6. Okay, for number 7, we're supposed to do a number of things. We want to get the Lewis structure and resonance structures. We want to get hybridization, orbital overlap, which resonance is the best, and bond length and bond order. So for this guy, we know that we've got 6 plus 4 plus 5 valence electrons plus 1 for the negative charge, which gives us 16 electrons. So there are basically 3 ways we can get octets on each of those atoms. And one way is a single bond to oxygen and a triple bond to nitrogen. Another resonance structure is a triple bond. Whoops, I messed that up. So I've got to get rid of these lone pairs here. We can have a triple bond to oxygen and a single bond to nitrogen. Boy, I'm all over the place here. Make one mistake and I just keep propagating. So here we've used 16 electrons and we have octets everywhere. And lastly, we could have double bonds to both the oxygen and the nitrogen like this. So they all have their octets. Now let's assign formal charges. Here we have a 0, and a 0 on the carbon. This is a -1 on the oxygen and a 0 on the nitrogen. This one is going to be, well, we've got 1, 2, 3, 4, 5. Basically, that oxygen has right to 5 electrons. It would need 6 to be neutral. So we would have a plus charge here, and this would be a -2. Here, that'd be a 0, and this one would be a -1. So we can say that we really don't like that resonance structure at all because it's got a 2 formal charge. So these two are the 2 best resonance structures. And out of the 2, which is the better one? Well, clearly this one, because the negative charge is on the more electronegative atom, which is oxygen. So regardless, if we look at the hybridization of this carbon, this is sp hybridized because it has 2 pair. This would be sp hybridized because it has 2 pair. And this would be sp hybridized because it has 2 pair. So what about the orbital overlap? Well, what they're really talking about is this. This is going to be an sp, and this is going to be an sp. And it'll be the same with this over here. Actually, I shouldn't say sp. This will be an sp, sp3, 2. And this is going to be an sp2. So actually, let me think about this for a minute. This is going to be an sp, and this is going to be an sp. So how do I get to that conclusion? Well, the answer is because here, when you have 2 or a triple bond, 2 of those bonds are pi bonds, which means you need 2 unhybridized p orbitals. And the way to get 2 unhybridized p orbitals is you take a s, a p, and a p, and you hybridize just the sp. So you get 2 of those, plus you have 2 leftover p's that can form pi bonds. So when your resonance structure has a triple bond, that means that that atom has to be sp hybridized. And so here, even though this isn't a very good resonance structure, you're going to have to say that that oxygen is sp hybridized. So the deal is the overlap, regardless of the resonance structure, is going to be an sp in the middle and an sp on either end. So the overlap is going to be an sp to an sp. Now, which is the best resonance? This is the best. So based on this, what are the bond orders and bond lengths? Well, the oxygen-carbon is equal to 1, and the carbon-nitrogen is equal to 3. Over here, if you look at this one, which is not the best, the oxygen-carbon is going to be a 2, and the carbon-nitrogen is going to be a 2. And chances are the real bond order is going to be somewhere in between 3 and 2 and 1 and 2 here. So that is the bond order. And what about the bond length? Well, we would expect that the bond order being smaller, that this might be longer and this might be shorter. Although it's hard to compare because we're comparing apples and oranges here, oxygen and carbon versus carbon and nitrogen. But as far as bond order goes between here, we'd expect that here, the OCN being the shorter, smaller bond order, this would be, I should say, since it's a bond order of 1, we would expect to have a long bond, and this would be a short one if we're comparing them that way. All right, let's look at N3 minus. So how many valence electrons for nitrogen? Well, there's 5. There's 3 nitrogens, and then we've got plus 1 more for the -1 charge. So that's 16 electrons. So here we also have nitrogen, nitrogen, nitrogen. And we can have a triple bond to one nitrogen and a single bond to the other. This would be a +1 formal charge. This would be a 0 formal charge. And this, since that's a negative, would have to be a -2 formal charge. We could also have the N double bond N like this. And here this would be a 0. Oh, excuse me, this would be a +1. This would be a -1, and this would be a -1. And we could also have one more resonance structure, which looks like this, where the triple bond is on the other nitrogen. And here we're looking at a +1, a 0, and a -2. Okay, so this one's clearly the best because we don't have any 2s. All right, this is the best resonance structure. So if we look at the bond, actually, if we look at the orbital overlap here, this guy is sp hybridized, and you would expect this guy also to be sp hybridized because it does have some triple bond character to it. Okay, now what about bond lengths and bond strengths? Well, the bond order for this guy is going to be a 2, and for this guy, it's going to be a 2. Now about the bond length, we expect them to be equal. Okay. Next molecule, N2O, which looks like this. So this is going to have 16 electrons, which means it will also have these possibilities. +1, +1, +1, -1, 0, 0, -1, and +1 and -2. So this is the worst because it's got a 2. So here, when we look at the hybridization, again, we're looking at sp, sp, and sp because they do have some triple bond character on the ends, which means that 2 of those have got to be pi bonds. And if it has 2 pi bonds, it has to have 2 unhybridized p orbitals, which means only an s and a p can be hybridized. The nitrogen is sp hybridized regardless of which one you look at. So the orbital overlap is going to be an sp to an sp. Now, which of these is the best? Well, I'm going to say that this is the best because we've got a -1 formal charge on oxygen, whereas here you've got a -1 on the nitrogen. Okay, so when we look at bond order and bond length, you're going to have to say that this nitrogen is going to be a 3, and this is going to be a 1, but this one, we're going to have a 2 and a 2. So what is the real nitrogen-nitrogen bond order? It's probably somewhere between a 3 and a 2. And how about the nitrogen-oxygen bond order? Well, it's probably somewhere between a 1 and a 2. All right. So here, this will be the shorter one because it's going to be kind of between a 3 and a 2. And this will be a longer one because it's a 1 and a, between a 1 and a 2. And remember, the higher the bond order, the shorter the bond. Last molecule is CO2, and you can draw 3 resonance structures for this. I'm going to start off with the best one. That's that one. And then I'll draw the other ones that are not so hot. So here you've got a 0, 0, 0. Here you've got a 0, -1, +1. And then there's one more where the triple bond is on the other oxygen. So you've got a 0, +1, -1. So this one is clearly the best. And we would expect the bond orders to be 2 here and a 2 there. And we expect them to be the same length and same strength. So overall, when we look at the 4 molecules we've just done, let's take a look and see what we've got here, because we kind of want to compare them all. So for the very first one, we've got 2 decent resonance structures. And here are the 2 decent resonance structures. And this is a -1, a 0, and a 0. This is a 0, a 0, and a -1, and this one is the best. So here, what do we expect for the bond order here? We expect it to be between a 1 and a 2. How about here? We expect it to be between a 2 and a 3. The next molecule, we have N3. And for N3, we ended up having 3 resonance structures, but one was clearly the best because the other 2 had -2s in them. So for N3, -1, we had this. Okay, and this is -1, and this is +1, -1, -1 for the formal charges, which when you add them all together equal a -1. So the bond order here is 2, and the bond order here is 2. So notice I'm only writing down resonance structures that are viable, and not the ones that are not viable. Okay, now let's take a look at the next one. We have N2O. And for N2O, we had 2 viable resonance structures, a triple bond between the nitrogen and the oxygen, or nitrogen and nitrogen. And then we also had a double bond like this. Lone pair, lone pair, lone pair, lone pair. Okay, so this is a 0, a +1, and a -1. This is a, +1, a -1, and a 0. Okay, so this one is the best because we have the negative charge on the oxygen. So when we look at the bond order between the nitrogen and the nitrogen, it should be somewhere between a 2 and a 3. And the bond order between the oxygen and the nitrogen should be somewhere between a 1 and a 2. And the last one we get is CO2. And there's clearly one best resonance structure, and that's this one, because they're all zeros. And here, the bond order is 2, the bond order is 2. And as far as the bond length goes, it's hard to compare apples and oranges. That is a carbon and an oxygen versus a nitrogen and an oxygen. So we'll just leave it at that. Okay, so that's number 7. Number 8. Which is isoelectronic with Bf4 minus? Well, we have to get the Lewis structures of each of these to see if any are isoelectronic. So here with boron, Bf4, you've got, let's see, 7 electrons for each fluorine. 7 times 4 is 28. 3 more for the boron, which is 31, plus that, which is 32 electrons. So here is Bf4. 32 electrons. And we're going to put a negative here. What about SiF4? Well, silicon is in group, let's see, 4A. So we've got 32 electrons. So that looks like it's going to be just the same as the one to the left, only we don't have to use a bracket because it does not have a charge. Now, what about SF4? Well, sulfur is in group 6A, so it's got 6 valence electrons. So we've got 28 plus 6, which is what? 34. So we're going to have sulfur, and we're going to put our fluorines around like this, because I know I'm going to have 2 left over after making octets on my fluorines, and I have to put them on the sulfur. So these two are isoelectronic because the distribution of the electrons are the same. So the reason this works is that they have the same number of electrons, and then they have the same number of atoms bonded together. So this has the same number of atoms bonded as these two, but it doesn't have the same number of electrons. These guys have 32 electrons, and this guy has 34. So if this is a 34 and a 32, they cannot be isoelectronic. So the answer is the SiF2 is isoelectronic with a Bf4 minus. So are SiF2 and SF4, or are SiF4 and SF4 isoelectronic? So we're asking about these two. The answer is no, they can't be. They have a different number of electrons. No, different number of valence electrons. What is the hybridization of SiF4? Well, this is sp3 hybridized, and SF4 is sp3 dehybridized. So why did I have to invoke the D? Well, because we have 1, 2, 3, 4, 5 pair. I'm going to circle them 1, 2, 3, 4, 5 pair. So S, P, 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 that's 4. And then D, that's 5. And we write it this way, sp3d. Okay, what is the relationship between bond order, bond length, and bond energy? Use C2H6, C2H4, and C2H2 as examples. Well, here is C2H6. And here is C2H2. And here is C2H4. And here is C2H2. So let's look at bond order. This is a bond order of 1 for the carbon-carbon, and we're looking at the carbon-carbon bond order. This is a bond order of 2, and this is a bond order of 3. When we look at the bond length, we expect this one to be the longest, and this one to be the shortest, and this one to be the middlest. So the higher the bond order, the shorter the length. Now, when we look at bond strength or bond energy, which one is the harder to break? This is the strongest bond, hardest to break. This is the weakest, and this is the middlest. So the more bonds you have, the shorter the bond is going to be, and the stronger it's going to be. Show how valence bond theory and molecular orbital theory rationalize the oxygen-oxygen bond order as 1.5, and I believe this is in O3. Let me double check here. So I'm going to go back, look at the homework, and in ozone, which is O3. Okay, so let's look at valence bond theory first. For valence bond theory, we need a Lewis structure. So we have 18 electrons because we have 3 oxygens. 3 times 6, 6 per oxygen is 18. So we're actually going to have this for one resonance structure, and this for the other. So in both resonance structures, we have octets on the oxygens, and we have a total of 18 electrons. All right, so when we look at the bond order here, you can see that this is a bond order of 1, and this is a bond order of 2. And this oxygen, I'm going to call this O1, OA, OB, and OC, because we have to understand that this resonance structure represents a molecule, and this represents the exact same molecule. So this oxygen is indeed that oxygen. They are the same. So here we have these 2 resonance structures, and neither one is better than the other, because here this is a 0, this is a +1, and this is a -1. This is a 0, this is a +1, and this is a -1. So they both have the same set of formal charges. One is not better than the other, so they're equal. So here, if you have one that has a bond order of 1 and one that has a bond order of 2, then the average bond order is going to be 1 plus 2 divided by 2 structures, which is 1.5. So that's how you rationalize the bond order using valence bond theory. You say, well, you know what? It's an average between these 2. Okay, now what about MO theory? Well, we have to use the right MO diagram, which is going to be the Christmas tree. Now, I'm going to make my Christmas tree a little bit different. I'm just going to do it like that. So this is an abbreviated, I'm sorry, I called it a Christmas tree. It's the palm tree. So remember, these on the outsides are pi's. And this is a 2p star, and this is a 2p. This is a 2p, and this one up here is a 2p star. This is a sigma 2p star and a sigma 2p. And this is a sigma 2s star and a sigma 2s. I'm leaving the 1s out, so I'm leaving the core out. So if I'm doing this, I only need to count, actually, I'm sorry, I made a mistake, because what I really want to do here is I want to look at just the p orbitals in ozone. So I have 3 atoms here, and you have basically in ozone, if you look at this, you basically have 2 pi electrons, right? So here we have these 3 p orbitals. These guys are going to make 3 molecular orbitals, and we're going to call them pi 2p, pi 2p, and pi 2p. Actually, let's look at the book. Clearly, I'm a little off track here. So I'm trying to remember this from the book, and I haven't reviewed it in a while. Chapter 9. So we're going to look at what the book says about hybridization for something like this. And here we go. This is valence bond theory for oxygen or ozone. And now here we look at the, we want to look at the molecular orbital diagram for ozone. Oh, and here it is. So I goofed a little bit here, and you can see that what's happening here is that for, I like to see what I'm looking at. You can see that for ozone, you actually have 3 pi orbitals that you're going to make molecular orbitals out of. And this is kind of interesting. So I'm going to get a new sheet of paper here. For the MO theory, for ozone, you have these 3 oxygens that have p orbitals. So this is a p orbital on each one of these oxygens. And when you make MO theory, molecular orbitals out of them, you actually get 3 that look like this. And so this is a pi, this is a pi, and this is a pi. And this is a pi 2p, this is a pi 2p star. And this is a pi non-bonding. That's what they call it. And so here, when we take the electrons that are in these pi orbitals, and so we are going to go reference this guy right here just for a moment. This guy, since it has 3 pair, has to be sp2 hybridized. This guy has to be sp2 hybridized because it's got that. But also, since we've got this guy also has to be sp2 hybridized so that the electrons can bounce around, so to speak. So the way to think about this is you can think, well, okay, so those are pi electrons, and 2 of these are pi electrons. So we've got 4 electrons we need to put into these pi orbitals. 1, 2, 3, 4. Okay. Now, this says that we basically got a pi bond between these 3 oxygens. So that also means if we look at the rest of the orbital theory, which we're not going to, you have a sigma bond here and a sigma bond here. So over all 3 oxygens, you're going to have 2 sigma bonds and only 1 pi bond, which is 3 bonds over all 3 atoms. So what is the average bond order between 2 atoms? If it's 3 bonds overall, it's going to be 1.5 bonds for 2 of the atoms. So again, this 3 bonds refers to all 3 of these. There is a bond order of 3 overall, okay? And so here, that means that on this side, it's 1.5, and on this side, it's 1.5. This is a much harder argument to make because we're not looking at MO theory with just 2 atoms. We're looking at MO theory with 3 atoms. Okay, that's number 10. And that is your answer key to the homework for Chapter 9, the gases.